Training data comes in the form of what we call training examples, in which each example is described by a set of feature and possibly also a label. So here we have a set of examples in the lines, and the rows represent the set of features. So we're talking about having data in the form of feature vectors x and a label y. So the label y will tell us whether there is a label attached to each example. An example of that, if you consider the set of fruits, fruit 1 from fruit n, you could have, for example, 10,000 fruits, and for each fruit we have a measurement of the length of the fruit, the width of the fruit, and the weight of the fruit. So this represents the feature values for the fruits, and we have here like 10,000 fruits, and each of the fruit will be labeled by the kind of fruit that we are talking about. So for example, the fruit number 1 of length 165 millimeters, width 38 millimeters, and weighing 172 grams is a banana. So given this configuration of data, we can do typically deploy two kinds of methodologies. So broadly speaking, machine learning methods can be classified into two categories, supervised and unsupervised methods. In the unsupervised learning, we learn models based on unlabeled data, which means that we don't need to know the label altogether, but we just need to deploy the methodologies on the left-hand side of this table, which is the feature vectors describing the examples. However, in supervised learning, we talk about learning models based on labeled data, which means that we need to use this information attached to each example to learn supervised models. In the unsupervised setting, we use training data as a set of examples, so we are going to only use the x's, right? And the goal is to find some clustering or segmentation of the data, which is to build a model that we call F, and this model will be mapping the input vectors, the x's, to some set of clusters. So we want to be able to say these examples belong to cluster, some cluster. Example of this includes find clusters in the population of data, for example, or classify fruits or species of fish. In our previous example, we could plot the data or the examples on a 2D space in which we could put the length of the fruit in the x-axis and the width of the fruit in the y-axis. So we would see naturally the bananas coming up together and the oranges coming up together. So this would be our group of banana would be here because they are longer and are thinner, and our group of oranges should lay out somewhere here. So we can deploy clustering methods in order to uncover this groupment in the data. In this case, we could discover these two ellipsoids that for each of the categories of fruits. In the methods that do unsupervised learning and clustering include k-means, Gaussian mixtures, hierarchical clustering, spectral clustering, etc. In a supervised setting, we can use examples with their feature vectors along with their labels. The goal is to, given a y label that is discrete, we simplify to y is equal to -1 plus 1, which means that we have access to positive or negative examples. So in our previous example of fruits, we could call all the bananas positive examples, and we could call all our oranges negative examples. So given examples along with their labels, the goal of supervised learning is to find a classification or a supervised model that maps the feature values that are in RD, given that we have D dimensions, into a class label that tells whether the fruit is a banana or an apple. Examples of supervised learning include approving credit yes or no for a bank, or your email, classifying a new email as a spam or a ham, or also, in our toy example, classifying bananas from oranges. So in general, we like to plot the data just to visualize a little bit. Here on two features, suppose we have again, let's say the length and the width or other kind of features. So we're going to plot all the bananas and all the oranges on the 2D space. We're going to put a plus on all the fruits that are bananas because we know the label, and we're going to put a minus on all the fruits that are oranges because again we know the label. The goal is to uncover what we call a decision boundary that separates the bananas from the apples, or positive from negative examples. So in this case, this is a possible decision boundary that tells where is the area of the bananas from the area of the oranges. Example of methods include support vector machines, neural networks, decision trees, k-nearest neighbors, naive Bayes, and many more. So you're going to see a subset of this, and you're going to see even more methods in your second course dedicated to machine learning. So classification can be linear, so just like in this case where the data is really well behaved, we have one side completely dedicated to positive examples, the other side only on negative examples. The decision boundary could be something curvy like this. It could be also some more complicated shapes like this case here or here. And if we have two or more classes, the decision boundary could separate each class separately. Suppose you have oranges, bananas, and apples. In this case, you have three classes, and you want a decision boundary that separates these three categories of fruits. Classification could be a little bit more complicated, such as this example here. Suppose you have all your positive examples in the middle, surrounded by lots of negative examples. It's not feasible to find a decision boundary that is linear to separate the data. The reason is that no matter how you would pick your line, the line would do a bad job at classifying positive from negative example. Wherever I've picked the line, it's going to do poorly on the data. So the idea here is that we're going to, as you can see, this data is in a two-dimensional space. We have x1 and x2 as features. It's possible through machine learning methodologies to put this data in another space, which is in this case a three-dimension, by transforming the features x1 and x2. And in this new space, we're going to be able to find a linear decision boundary, whereas in the initial space, the decision boundary was actually this ellipse around the positive examples. So in this case, we're going to kind of pull this positive example out to make them in a 3D, and then find the linear separation between positive and negative example. This is something that is possible with machine learning new methodologies. So there's another category of supervised learning, which is regression. In this case, we still have our feature values and labels, but the labels happen to be actually in R, which means that instead of having a label plus or minus, we would have a real value that tells, for example, what's the amount of credit. In this case, what we want to recover is, what we want to find is rather a function or a model that goes still from RD, from the d-dimensional space, but that would map this to a real value, which is the label that we have. We call F in this case a regressor rather than a classifier. And examples of that include, for example, for a bank to regress to find the amount of credit. Or if you have, suppose, the length of the fruit, can we try to build a model to predict or to find the weight of the fruit? As an example, suppose you have data in which you have one feature. It could be, for example, the length of the fruit, and we want to be able to predict the weight of the fruit. So it's possible to plot the data. In this case, we don't have pluses and minuses, but we just have data points for which we want to predict to map the weight of the fruit based on the features that we are considering. Other examples include doing a regression to predict the income in function of age, or, as I said, the weight of the fruit in function of its length. So in this case, we're going to try to fit some curve through the data points. This is the first possibility, so we could try to fit in a linear function through the data points. We could also try to find something curvy that would map the shape of the points, or finally really try to find a more complicated kind of function that goes through all the data points to really match the data exactly. So in a typical setting, what we do, whether it's in a supervised or unsupervised, is to do a training and testing scenario in which we start with training data. So could be feature values with label, yes or no, for the label depending on the method. We deploy some machine learning algorithms, so we cited some of them, support vector machines, k-means, etc., to build what we call a model or function F. Then, given this model has learned from previous experience or from previous data, we're going to try to use it to make a prediction. So suppose we have, in the case of a bank, in the bank example, suppose we have the income, the gender, the age, the family status, and the zip code of a customer. We want to be able to use the model to predict, in the case of classification, whether the patient should get a credit, yes or no. And in the case of regression, what will be the credit amount that the bank should give to the customer? Other examples, we could plug in the length, the width of the fruit, and predict the kind of fruit, whether it's a banana or an orange or whatever. Okay, so this is the typical setting in which we want to do a training, build a model, and this model is readily available to be tested on new instances that were not used for training.